Good evening, Algebra 2 kids. How are we all doing? I hope pretty good, because today we get to talk about products with radicals, and they are actually pretty neat. They're just kind of like our exponent rules that we used to have back in the power unit that we did. So first thing you need to know is your root of a product theorem. You're going to want to make sure you write this down. It says for any non-negative real numbers x and y, so of course they have to be positive here, and any integer n being bigger than or equal to 2, we know, this we already know about. When we have an exponent, we can distribute it to both bases here, and we can also do that with radical form here. We would say the nth root of x times y would be the nth root of x times the nth root of y. So we can break these radicals down and simplify them if we can. That's what this actually allows us to do. And it comes from the fact that this rule we already knew, we just translated it into radical notation here. So make sure you get this down, and let's see how it's used in the next example here. Alrighty. First things first, we want to find the product of the cube root of 18 and the cube root of 12. So we can go about this two different ways here. Sorry, let me get my pen going. Alright. We could put them together and then take the cube root, or if we know the cube root of 18 or we know the cube root of 12, then we can go from there. So 18 and 12 not really coming to mind to me right now. So let's actually multiply them together, because cube root would have to be something times itself 3 times to get 18. Not cutting it for either 18 or 12. So what we're going to do is we're going to rewrite this. So we have the cube root of 18 and the cube root of 12. We're going to multiply them together. So we have 3, or the cube root, we're just both going to put them under one house here. So 18 times 12, and then we got to actually do that. So let's grab our calculators here. All right. So 18 times 12, okay, is 216. So we need the cube root of 216. And you might know that, you might not. It's actually 6, but I'll show you here. How do we do it in here? Remember, we go math, option 5, and then put in 216. If we wanted to, actually, let me show you this. We could actually pull this answer, just like we always do. And we'll be able to do it. There we go. And it's 6. So the cube root of 216 is 6. Now, the cube root of 18 and the cube root of 12 don't exist by themselves. So let me show you that. So cube root of 18 is a decimal, and the cube root of 12 is a decimal. Oops, darn it. Of course 11 would be, but we really want 12. Oh my gosh, I did it again. 12, there we go. It's still a decimal, but together, after you multiply them, they actually produce the number 6. So that's something we like a little bit better, I think. Example 2. Assume that x is bigger than or equal to 0. Of course, it's positive again. Just a fancy way of saying it. Write the 5th root of 5x times the 5th root of 3x squared as a single radical. So again, we're going to take this guy, and since they're both 5s here, you can't do it if this was a 5 and let's say this was a 4. They have to be the same. You can only take the 5th root of two things separately as long as they're the same as the 5th root together. Okay, so let's put them under one house here, one big radical. So then we have 5x times 3x squared. And now that these are together, I can actually multiply. So we can do 5 times 3, so the 5th root of 5 times 3 would be 15. And then x to the first times x squared, we can multiply those together, which would be x cubed here. So then we have 15, or the 5th root of 15x cubed. And then you would always want to check, can I simplify that anymore? Well, can I do the 5th root of 15? I don't think so, but it doesn't hurt to check. So let's do 5th root of 15. Yikes, no decimals, so we don't want that. And then if you had like the 5th root of x to the 5th power, well, those would kind of undo each other, so you could do that. The 3 doesn't, though, so we'll just leave this as such. It said as a single radical, and that's what we have. So now we are done. Okay, again, suppose n is bigger than or equal to 0, meaning it's positive. That's all that this means. We're going to simplify this. Okay, so last time it didn't get to simplify. This time it does. So we're actually going to do it. So we have 4, the 4th root of 16, n to the 12th power. And just like we were doing before when we were learning our power rules, I always said, think of these two things separately. Same idea here. Can you take the 4th root of 16? Can you take the 4th root of n to the 12th? So even if it helps you, now you're going to get good so that you can skip this step, but if it helps you for now, my goodness, just break it up anyway. Okay, we're just doing the backwards of what we just did, which is totally allowed. All right, so the 4th root of 16, let's see what that is. I have a feeling it's going to be 2, but let's just double check. Oop, there we go. 4th root of 16. Yes, 2. Fabulous. Okay, so that comes out even. We'll want to do that. So this is equivalent to 2, so we just write a 2. And then if I take the 4th root of n to the 12th, well, let's rewrite that in power notation. So n to the 12th over 4 is what that would be. Okay, so 2 times this junk. So n to the 12th over 4. Well, 12 divided by 4, we can totally do that. So 12 divided by 4 is 3, so we have actually 2n to the 3rd power. And that actually reduces quite nicely. If it didn't, you wouldn't want to do it. You know, if you got n to the 3.692 power, you don't want to do that. But since it turns out to be nicely 3, that's much, much simpler than this guy up here. Okay? So this is, these two, if you can believe it, are equivalent. They are just in, this guy's in simplified form, that guy's in very complicated form. Okay? Alrighty. Example 3 says, suppose that p is bigger than or equal to 0. Again, that just means it's positive. We're going to rewrite the cube root of 875p to the 7th power. Okay? These numbers look nasty, honestly, they do, because guess what? They're odd, which is one thing we don't like. So we have 875. Can we figure out the cube root of that? I don't know. And then we have p to the 7th. So there is a way to simplify this, and I'm going to show you how. First things first, I would always check see if 875 was a cube root at all, because that's what we're working with. So 875, is that a cube root? Yikes, it's not. Bummer. Okay, so essentially what we want to do then is we want to break down, we're going to factor 875 to see if it's a large number. We could probably take some cube root out of here. I just don't know what yet, okay? So let's go ahead and take 875. And if you remember making like those little factor tree things when you were a kid, it's kind of like that, although I'm not going to write it like that because that becomes a little bit confusing. So let's get rid of these, and it's the same concept, exact same concept, except I organize my work a little bit differently here. I just do an upside down division sign, okay? That way all the stuff I divided by runs along the outside here. So the first thing, I want to think of all my prime numbers again. And prime numbers, remember, are 2, 3, 5, 7, not 9, but 11, etc., etc. Okay, basically numbers that cannot be divided by anything but 1 in itself. So numbers whose only factors, sorry, whose only factors are 1 and itself. That's what prime numbers are. So 2, 3, 4, 2, 3, not 4, excuse me, 5, 7, 11, etc. So let's start with these. You always start with the smallest one. Is this number divisible by 2? Absolutely not, because it's not an even number, so that's not going to work for us. So we move up to the next one. We check 3. Is 875, come on calculator, is 875 divisible by 3? Divisible by 3. Let's see here. Nope, not evenly. So we move to the next one. Check 5. So is 875? It should be, because it ends in a 5. Divisible by 5? Bingo. So that means we put a 5 here and a 175. So now don't go back down to 2 and 3. Neither of those worked for us, so we're stuck on 5 right now. But don't move to 7 either until 5 stops working for you. So we're going to take 175 and see if we can divide it by 5 again, which we should be able to. So divided by 5, boom, we get 35. So I'm going to put another 5 right here, and we get 35. And then, well, it looks like 5 is going to work again, so try 5 again. All right, 5 does work. So we're going to divide this guy by 5, and we get 7. Now, we could keep going here, but we got a prime number, so we know it's not going to divide into anything but, you know, 7 and 1. So we're going to stop here. So essentially, the prime factorization is what this is called. So the prime factorization of 875 is, and you just write all these out. You say 5, well, how many 5s are there? To the third power, or times 7, okay? So we have 5 times 5 times 5 times 7, and that gives us 875. Don't believe me? Try it. Do, excuse me, 5 to the third power times 7, and boom, we get 875. Okay, so we're going to replace 875 since it's equivalent here. We're going to replace 875 with 5 to the third times 7, which seems weird at first, but just trust me here. So we have 5 to the third power times 7. And then we have, well, let's separate this right now. I'm going to say cube root of p to the 7th. We can separate that because we can separate the 875 and the p. Okay, so get rid of the p's for right now. Let's focus on this guy. And furthermore, I could even break down this guy because these are two separate things, 5 to the third and 7. So what I'm going to do is I'm going to say cube root of 5 to the third power times the cube root of 7 times the cube root of p to the 7th power. Okay, so, oh, look at this here. If I have the cube root of something being cubed, get rid of them. It's just what's underneath. So this becomes a 5. Voila! Which is why we did the prime factorization, and why the key here was that we ended up with 3 5s because we're taking the cube root. So I knew, and you should maybe caught on as well, that that was going to be able to come out of those parentheses, or excuse me, that radical there. So you're going to want to watch for stuff like that. Okay, now 7's got to stay because it doesn't have a cube to cancel with, so we say cube root of 7 still. But here, we can still do something with this. I'm going to break this up, and you're going to get better at these, I promise, at recognizing these patterns. I'm going to break this up as the cube root of p to the 6th power, and then the cube root of p. Now, can I do that? Well, yeah, if I put them back together, I have 6 p's here, I have 1 p here. We add when we multiply our bases. So when we add these together, that's power of 1. That makes 7. So I can break it down to that. And the reason I did that was because then I can simplify this guy here. Because 6 is divisible by 3. So if I take the cube root of the 6th power of p, well, that would be 6 divided by 3. That'd be p squared times cube root of p. Okay, that's what the p's. Now we still got to bring this stuff down. So 5 times the cube root of 7 times p squared times the cube root of p. All right, so this is getting a little bit messy. Let me get rid of all this stuff because we're done with it now. We can still simplify it a little bit more. This is getting a little tough, so if you need to rewind it right now and rewatch how I got from here to here, please do so. I hope this makes sense to you. If it does, keep watching. If not, rewind it. That's the beauty behind videos. But now we're going to take this to the point where we can say, okay, this stuff is outside of the radical, and so is this. So let's just group that stuff together. That would only make sense. So I would have 5p squared. And then the stuff that's underneath the radical, which would be this stuff and this stuff here, let's group that stuff together. And in fact, let's even put it under the same square root, or excuse me, cube root. So we have 7 times p, which is going to be 7p here. Okay, so believe it or not, I know it just has to rewrite, so they didn't use the word simplify, so you might even think that's not simplified, but this is actually the simplified version of this. These two things are absolutely equivalent. This guy, we just pulled out what we could from that cube root and left what was left over, and sometimes that happens. Alrighty, so this would be our simplified version. Alright, so we have one more example and something to talk about here, so please tune in to the next video. It'll be short, I promise. I know this one was almost 15 minutes, but bear with me. You're almost there. Yay! Yay, radicals!